Hello everyone, I am Zhou Yuwei, a PhD student from Media and Network Lab, Department of Computer Science and Technology, Tsinghua University. It is my honor to introduce my work about CurBench, Curriculum Learning Benchmark. First, I would like to introduce the background of this work. Curriculum learning is a training paradigm where machine learning models are trained in a meaningful order, inspired by the way humans learn curricula. Due to its capability to improve model generalization and convergence, curriculum learning has gained considerable attention and has been widely applied to various research domains. These two figures illustrate the basic concept and framework of curriculum learning, cited from two related surveys, respectively. Currently, an open issue in this field is how to benchmark the diverse curriculum learning methods. The increasing number of works pose challenges in terms of comparison and evaluation, mainly due to the difference in the experimental setups, including datasets, backbone models, and settings. This table lists three examples. DCL and DDS use the same wide ResNet 2810 model, but perform experiments on different datasets, CIFAR 100 and CIFAR 10 respectively. Similarly, DICL and CBS leverage the same ImageNet dataset, but employ distinct models, ResNet 50 and ResNet 18 respectively. Moreover, while MCL and ARRE utilize the same NIST dataset and the LearnNet model, they adopt different settings, standard and imbalanced labels, respectively. Consequently, their experimental results cannot be compared directly, which makes it challenging to conduct a fair evaluation. Till now, researchers have made notable efforts to evaluate and summarize existing works. From a theoretical perspective, there have been surveys covering general curriculum learning as well as specific ones for graph and reinforcement learning, all of which manage to formulate and categorize relevant methods comprehensively. Although they offer valuable theoretical insights, current surveys do not incorporate any practical implement or experimental results. From an empirical perspective, there has been an open source library on curriculum learning, which reproduce multiple related methods through a unified framework. Although it provides empirical results of the implemented methods, this library only supports the classification task on CIFAR 10, limited in experimental setups. In order to address the absence of benchmarks in this field, we propose CurBench, the first benchmark for systematic evaluations of curriculum learning. CurBench includes 15 datasets spanning 3 research domains, 9 backbone models, 3 training settings, and 2 evaluation dimensions, with a toolkit for reproducing 15 core curriculum learning methods. This table reports the statistics of 15 datasets adopted in CurBench, which covers a wide range of scales across 3 research domains, CV, NLP, and graph, in 3 settings, standard, noise, and imbalance. Noise 0.4 means 40% data samples are independently attached with random incorrect labels. Imbalance 50 means a ratio of 50 between the number of samples in the largest class and that in the smallest class in a long-tail dataset, where the number of samples for each class follows a geometric sequence. The imbalance setting is not applied to NLP and graph datasets which are imbalanced originally. This table overviews the backbone models that we employ in CurBench. All the values in the last column are approximations because the number of parameters varies depending on the input sizes and output classes. All of the models are commonly applied to the aforementioned dataset, and they are distinct from each other in mechanism and model size. To robustly evaluate the curriculum learning methods, we established the 3 settings, standard, noise, and imbalance. To ensure a comprehensive analysis of existing method, we consider two evaluation dimensions, performance and complexity. To facilitate the use of our CurBench, we develop a toolkit. It is composed of 5 modules and offers a unified and complete pipeline from initiation to evaluation, aiming for easy implementation and reproduction of curriculum learning methods. This figure showcases an example of noisy C510. This table presents the overall performance with and without curriculum learning on the different combinations of backbone models, datasets, settings. These are the main results on CV and graph datasets. These are the main results on NLP dataset. It is observed that there has been no such method that outperform others all the time, and effectiveness depends on specific scenarios. This figure shows the performance of curriculum learning methods on datasets with different noise ratios. It is observed that methods by teaching transferring have edges in noise settings. This figure shows the performance on C510 with varying imbalance factor. It is observed that all methods achieve similar performance on different imbalance ratios, and methods by reweighting perform relatively well in imbalance settings. This figure shows the time and space complexity of each method in the case of ResNet 18 and C510, measured by GPU training time and maximum GPU memory consumption. It is observed that methods involving gradient calculation and extra-learnable networks generally have higher time and space complexity. Furthermore, we dive into our benchmark organize experimental outcomes, conduct in-depth analysis, and obtain some interesting findings. The first is there has been no such method that outperforms others all the time, and the effectiveness depends on specific scenarios. The second is curriculum learning brings more significant improvements in noise settings than in standard and imbalanced ones. The third is methods by teacher transferring have edges in noisy settings, while methods by reweighting perform relatively well in imbalanced settings. The last is that methods involving gradient calculation and extra-learnable networks generally have higher time and space complexity. Our contributions are summarized as follows. We've proposed CurBench, the first benchmark on curriculum learning, to best of our knowledge. We conduct extensive experiments to impartially evaluate and compare the performance and complexity of existing curriculum learning methods on the various experimental setups. We make in-depth analyze and demonstrate interesting observations on curriculum learning based on empirical results derived from CurBench. That's all. Thank you very much for listening.